If we have two lenses, for example, if you have a telescope or a microscope, something that has a system of lenses, it turns out the way to solve the problem is actually pretty easy. Let's do an example to show you how to do it. So a telescope. Telescope, we're looking at a refracting telescope, so it's constructed with two lenses. The lenses are separated by 25 centimeters. Both lenses are converging.
Are we supposed to know that?
Now you are, because I've just told you. The objective is the one that the light will pass through first. The eyepiece, aptly named because that's the one you're looking through. So the light's going to come through the objective, come through the eyepiece into your eye. So our object is somewhere over there. And certainly can't draw it to scale since in this case it's 100 meters away. The focal length of our objective is 20 centimeters in this case. The focal length of our eyepiece is 5 centimeters. The focal lengths lie on top of each other. The focal length of the objective is 20 centimeters from the objective. Focal length of the eyepiece is 5 centimeters from the eyepiece. So that puts them in the same spot. Okay? Now it turns out, all that's happening is light is coming through, this lens starts to converge it, this lens finishes converging it, it goes into your eye converges it, and forms an image on your retina. Mathematically, to deal with two lenses, we look at what the first lens will do by itself, figure out where the image will be due to this lens by itself, and that image we treat as if it were the object for the second lens. Okay? So here, for the objective, we know object distance for the objective is 100 meters. We know the focal length of the objective is 20 centimeters. We need to be consistent in our units, so we'll make that 0.2 meters. So we can easily find the S prime for the objective using our top equation over there. So 1 over 100 plus 1 over S prime is equal to 1 over F. Solving for S prime, we get 0.2004 meters. Now you want to keep a number of decimal places on these, because if you don't, you end up getting a really screwy answer. So what that means is our image, we get a positive value, which means it's on the back side of the lens. 0.2004 means it's just over 20 centimeters from this lens. So our image barely passed the focal length. In terms of whether it's upright or inverted and how big it is, we need to know the magnification. So the magnification of the objective will be negative S prime over S. So negative 0.002004. Magnification, it doesn't matter by so much how many decimal places you use. Negative sign means what? It's inverted. So if our original object was our traditional upward pointing arrow, this is a downward pointing arrow, and it's really, really small compared to whatever the size of the original object was. Okay. Now, mathematically, realistically, the light's just passing through both lenses and forming an image for you. Mathematically, we're going to find this original image, the image from the objective lens. This is going to become the object for our second lens. So S for the eyepiece. S for the eyepiece is not 0.2004. This is the object, but where do we measure object distance from? object to the lens. If we want to know S for the eyepiece,
Oh, it's distance minus.
we need to know how far we are from the eyepiece. So 0.25 minus 0.2004, 0.0496 meters. We know the focal length of the eyepiece is 5 centimeters, so 0.05 meters. So we can find S prime. Using the top equation again, 1 over the 0.0496 meters plus 1 over S prime is equal to 1 over F, the 0.05 meters. S prime ends up being negative 6.2 meters. Negative sign means a virtual image. Which side of the lens will that image be on? Same side as the object. So our image, this final image we get, measured from this lens, certainly not drawn to scale, 6.2 meters away. Okay.
Oh, so that's where we perceive it.
That's where we would perceive it
Okay,
being.
that makes sense.
Mhm. Magnification of the eyepiece, negative. S prime is negative 6.2 meters. S is 0.0496 meters. So we get positive 125. Positive sign means the object and the image have the same orientation. Okay. So our final image is upside down still, relative to the original object. And that's because the first lens flipped it over. This lens keeps it the way it was. This lens makes it 125 times bigger. But it was this much smaller from the first lens. Total magnification you want to find totally what is happening, you simply need to multiply the two magnifications together. So total magnification for our final image is negative 0.25. Negative meaning the final image is inverted relative to the original object. The 0.25 meaning the final image is 1/4 the size of the original object. Now, I don't know about you, but when I've looked in a telescope, what I'm looking at looks a lot bigger than if I look at it with my naked eye. You have to think of this, the size of the image compared to the actual size of the object. If you're looking at a building that's 100 meters away, it's not going to look very big. But 1/4 of the size of the actual building, up close, looks a lot bigger. When you have telescopes and microscopes, they're not telling you the true magnification in terms of how big the image is compared to the size of the original object. They're giving you what's called an angular magnification. Imagine looking at the moon. You can see the moon at night right now. It's nice and pretty. If you drew a line from your eye to one side of the moon and another line to the other side of the moon, there would be an angle in there. Now imagine looking through a telescope. The moon's going to look a lot bigger. Imagine drawing a line from your eye to one side of the image of the moon and the other side of the image of the moon. That angle is going to be bigger. Angular magnification is simply the angle if you were to look at the image versus the angle if you were to look at the original object. It looks bigger because it's a lot closer. The actual true size of the image is still a lot smaller than the actual size of the moon. Okay. I don't remember the equations off the top of my head, but these angular magnifications for both telescopes and microscopes are in your book. They do relate to the focal lengths of the lenses. So this angular magnification is given for you in the text itself as well, so you can look those up. So using two lenses actually isn't too hard. We just end up having to make our calculations twice. We need to find where the image is for the first lens. That becomes the object for the second lens. You have to remember that you need to find the distance from the second lens to know your object distance. You can easily find where the final image will be. Okay? So, not too hard having two lenses. We'll do another example of this tomorrow, though, so have a little more practice.